Recording has started.
Alright folks, let's get into the next module, which is Wireless LAN Concepts. So this one is where we cover wireless and introduce, instead of standalone access points that are basically fully configured singly, we introduce the managed wireless management system with a device called a wireless controller, and this is used to manage multiple access points, and it's quite an interesting little device. We'll have a look at how channels work. These are discrete channels of signal, so it's like tuning in your radio station, if you like, a radio station. So you tune your access points and your devices in to that particular channel, and you get hopefully a clear signal. We'll look at the various potential threats that wireless networks face, and then we'll describe ways of mitigating those threats within the security mechanisms of wireless. This is the first of two chapters on wireless. The next chapter will be in actually programming what we've talked about today. So we'll go through the theory components of how wireless works today, and in the next session we'll go through how you program these devices to handle the scenarios we talk about. So, as most people already know, wireless networks are networks that do not have wires. Strangely, that's why they're called wireless. Now, these come in various shapes and forms. So we go from little Bluetooth networks up to satellite networks and anything and everything between that deals with radio frequencies that allow us to have mobile devices. So we have a few categories. We have a personal area network, a local area network, a metropolitan area network, and a wide area network, just like we basically do with normal networks, but we stick a W in front of it because it's wireless. So what's the difference between them? Basically, the different standards and the different ranges. So most common frequency that is used is the 2.4 gigahertz frequency, and our personal area networks tend to be about 5 meters, between 5 and 10 meters, depending on the signal strength and interference. Now, the frequency used for these networks are combating all the other free wireless devices around, because 2.4 gigahertz is an open frequency worldwide, so lots of devices will be using this frequency. Now, with the introduction of Bluetooth many years ago, came wireless headsets and microphones and all that sort of lovely stuff that we take for granted today. But the new kid on the block is the Zigbee network. Now, this is based around the Internet of Things. This is for little devices that pop up and give status reports basically and then shut down again. So they're not on full time for the vast majority of them. They basically pop up, tell the information, check in, statuses and that sort of thing, and then shut down. And they tend to use a meshed wireless network. So next one there is the LANs. This is the ones that will take us to about 100 meters, give or take 50 odd meters or more, depending on where they're set up and what's around to interfere with them. Now this is where we break off into two frequencies. We have continue for the 2.4 gigahertz, but we add 5 gigahertz into this mixture as well. And we'll look at the various elements that this comes in. Next up is our metropolitan version, which is where we start using microwave dishes and things like that to give us a greater distance and a greater coverage. Then with the wide area networks, this is where we basically start looking for our satellites and things like that. So this is also where mobile phones fall into categories as well. Now, I think this is hilarious. One of these days I'll remember to change it. Can you see the typo? Yeah, let me give you a hint. It's in the second line. Bluetooth does not go 100 meters. It'd be pretty impressive if it did. But that's neither here nor there. So, as we said, 5 to 10 meters, and this is our personal area network. It's a low energy mesh type topology, which means it sort of links to everything else, and it supports basic rate and enhanced rate streaming. So basically what this allows us to do is to provide good point-to-point audio streaming. Now this is where most people use it, is with their headsets and that for the mobile phones, and even headsets for desktop phones will be used quite a lot. Next one there is WiMAX. Now this is where the microwave towers with their dishes come into play, and we get about 50 kilometers if we don't have things in the way. WiMAX requires clear line of sight, so trees and high buildings and that will get in the way and provide us with problems. Next is the one we use every day, the mobile networks. Now these carry, as you know, both voice and data, and there's various standards in use around the world. So you've got GSM, CDMA, and there's going to be others currently, variations, so on and so on. It's technology, so it changes and adapts as the years go on. Lastly, the satellites. So as you probably already know, we have various satellites in geostationary orbit, and they too need clear lines of sight down to the Earth that they want to communicate with, and they also need satellites to dishes on terrestrial dishes as well as the ones in orbit to function. Now, the problem with satellite is very large delays, right? Because it takes a physical amount of time it takes to get a signal from the ground up into orbit and then back down. That's what takes all the time. So it adds a huge delay into it. Here's a table of all the relevant standards, their frequencies and bandwidth. Now these bandwidths, as you'll look at it and go, we went from 2 megabits per second, now we're talking about 1.3 gigabits per second using 5 gigahertz. And then when we start moving off into AX, which uses 1 gigahertz and 7 gigahertz frequencies, this is a high efficiency wireless network that opens up a huge new ball game for the future. So people from AC down, so AC N and G, probably be around for a while. Now, most people probably won't be having G at the moment, but you certainly still have N and AC floating around. And G's around. B, yeah, not so much. A, you'd be pushing it. But the thing is, these standards have been designed with backward compatibility because everybody knows that most people, especially businesses, do not throw out kit unless they absolutely have to. So these are backward compatible. Now, the problem with wireless and its backward compatibility is if you put a B network card into a network that is connecting via an N access point, it'll downgrade itself to the lowest common denominator. So the entire efficiency drops down to support the lowest and oldest card. And basically here gives you a visual representation of the frequency in use and what types of devices use the frequencies at the spectrum. So the ultraviolet is our visible light sources effectively, and then you know, on the left here we've got radio waves, so we've got the radios, the TVs, microwaves, satellites, remote controls, which are infrared, then X-rays and gamma rays, and next slide. This one is, that's alright, Brad. I just looked up at the message board, so welcome. The International Telecommunications Union and IEEE, the Institute of Electrical and Electronics Engineers, and the Wi-Fi Alliance are all members of separate organisations that work together in support and maintenance of the standards. Obviously, some have more than others in as far as influence and regulation control, but these are the three main bodies that govern our wireless communications around the world. The Wi-Fi Alliance is all our various vendors agreeing to adhere to the standards and to make sure their equipment works together. So it's a big co-op of vendors working together to make sure their devices work together and provide usability and functionality without any hiccups. Now, a wireless network is not that much different to a wired network that we've all grown to love over the many weeks of the course. In this one, we substitute the media from a copper or a photogenic type cable to something that is not visible and doesn't have any physical connections between interconnected devices. So we still need a network card that provides that layer 1 and up connectivity. So it's the interface between the physical and the software, just as every other network card is, but this time the media is radio waves. The home router is what you're used to seeing, is a access point, a switch and a router combined into one device, and provides us with a default gateway to the internet and other network devices, as well as paying the connection from wireless and wired. Access points are wireless network interface cards. They come in different shapes and sizes and look to work differently, but they don't. They are all network interface cards. It's just that we call them slightly different names because we want to be specific about what devices we're talking about. So when we're talking about a wireless access point, this is the equivalent of a hub in a wired network, which connects our wireless network interface cards into it. So the access points, generally speaking, will be connected to a wired network. Now you can extend your range of your access points by putting in another access point within the frequency range, and this is called bridging, but it's not the best solution. Next up is autonomous access points or controller-based access points. Now, as I said earlier, autonomous ones are where we configure them as standalone individual devices. There's basically no handover between various access points, as each one is its own unique device, and you'd have to deassociate from one, then reconnect to another. When we move into controller-based access points, we start getting into the easier place of doing base handovers between the various devices, and we can control it from a central location through the controller. Excuse me. We use a lightweight access point protocol to communicate between the controller and the access point. These are known as lightweight access points because most of the heavy lifting is done in the controller. Next up is our aerials and the way they work. Now, your standard aerial is omnidirectional. It means it provides 360-degree cover, and it's like a big globe. Next is directional, which uses a shaped dish behind the aerial, and it forces the radio waves to deflect and point in a single direction, which gives us a directional antenna and a stronger signal in a specific direction. Examples are like the Ieee antennas that you would have for your TVs on your ceilings in your roof space. Next is the multiple input and multiple output, which can be up to 8 aerials, which increase our potential bandwidth and frequencies. So each aerial would be using a slightly different frequency, and we'll be using the reflections and refractions of the environment to increase throughput. Next up, we're going to be talking about topologies. We have ad hoc mode, which is like just devices connecting directly with each other, so peer-to-peer network. Infrastructure mode is where we have a structure like a wired network that an access point connects into. And then we've got the mobile phones using the tethering, which is using it as a wireless hotspot or using a cable to connect the mobile into. Service sets are either basic or extended, and what the difference is, a single access point is a basic service set. All devices connect to the same service set and cannot communicate to other devices in a different service set. So an extended service set is where we use multiple basic service sets interconnected with wired distribution, and this way the devices can communicate between the service sets via the wireless network. Our frame structure is a little different, but it's still Ethernet. But because we have a different media, we have a different header structure, but it's still the same frame format. So we have header, payload, frame check sequence, because that is Ethernet. But what we do is we have different fields in it to control the messaging between the access points and the individual devices and their addressing. Now, we can't detect collisions in radio frequency very well, but we can avoid collisions. The way we do this is the individual devices continuously listen to the carrier signal that multiple devices are using, and the access point is used to control messaging. So when a device wants to send information, it requests the access point to give it authority to send. The access point will grant access by sending a clear to send message, and then the device will send the message. If it doesn't get a clear to send, it does a random back off, just like a wired network does on collision. So we have a few different steps within wireless. We need to discover the access point to be able to get the service. We then associate with the access point and authenticate. Now, depending on what you read, depends on the order. So we need to associate before we authenticate. If you just looked at the graphics here, you'd think it'd be the other way around, but it's not. Excuse me, I'm losing my voice this morning. So, some key things we need to have lined up before communication can occur between a wireless device and an access point. We need to be on the same service set identifier. We must authenticate using passwords. We need to use the same standard, which we'll go through. Well, we've already gone through that big matrix of standards that you saw covering various frequencies and different speeds. So they've got to be compatible and be able to agree on using that mode. Next, we have to have the security parameters match, which is agreeing on the type of encryption. And next, the frequency band or channel settings. So, excuse me, very poor of me to yawn in the middle of the lecture. It's that exciting. I know I'm putting myself asleep. Alright, so what's happening in passive and active modes is where the SSIDs are always sent or requested. Now, the beacon always contains an SSID, and the beacon always is sent at a periodic spacing. Now, a wireless device can send a probe, which is saying I'm looking for this service set identifier, and then it's basically advertising itself saying I want to connect to this service set, this is the standards I support, and then the access point responds saying, yeah, that's me. Here's the agreed standard that we're going to use. This is the security settings you must comply to. Whereas a passive mode is where the access point does all of the initial communications and the wireless client just selects it and joins it. So, CapWAP. And yes, I know that's going to be a whole field of dad jokes around that. I'm going to control myself today, honest. Alright, so IEEE standard protocol that allows our wireless controllers to communicate with our access points. It has extra bits in it that allows lightweight access point protocol to do all that lovely control. So ports 5246 and 5247 are used, and then the various protocols under IP being protocol 7 and 136 under IPv6. Next up, the functions. So the access point is, as I said, like your hub. So it is responsible for the beacons and probe responses. It acknowledges all packets and retransmissions. It does all the frame queuing and prioritization before sending it across the wired network. And it does the encryption and decryption of the layer 2. Now, the controller handles authentication. It confirms association and deassociation or reassociation of clients. It handles the handoff between one access point and another if you're roaming. It does frame translation between the various protocols because we're dealing with different media, so therefore it has to be translated. And it will terminate the traffic on a wired interface. So what are we talking about? We have the wireless controller having an encryption controlled tunnel with the access point that the data does not see. The data can be optionally encrypted and protected between the access point and the controller. So what happens is the controller has control over the access point and control over the flow of data from the access point into the network. Now, while it's in control, it's known as a connected mode network. When it's not in control, in other words, the controller is unreachable, the access point can fall back to a locally accessed authentication, but it will only have local traffic access. So it wouldn't be able to gain full wireless connectivity through the full wired network. This next section is dealing with all the various frequencies. I won't bore you with reading out the wall of text in front of you at the moment, but these three techniques of handling modulation, which is the signaling across the radio waves. So this is how the various techniques of sending messages across RF occur. In the 2.4 gigahertz range, we basically only have 3 clear channels that will not overlap with each other if you lay it out across interlaced access points. So there's 11 channels in total, and the way they work is each channel is 22 megahertz in width, and they're separated by 5 megahertz steps. So one starts at 2.2 gigahertz, and you step it up by 5. So it goes 2.25, 2.2, it'd be 2.3. Go on. You know what? So what we end up with is a set of overlapping rings, and 1, 6, and 11 do not overlap with each other. So we can lay these down in a pattern, alternating the channels between each access point, and have clear, concise zones of non-interference with each access point. Same thing occurs in the 5 gigahertz range. These are 20 megahertz channels instead of 22, and we have non-overlapping channels 36, 48, and 60. And yes, I have not slept this evening, so it's starting to tell. So this is where you deploy your access points. So what you need to do is measure your building and make sure you do not overspace your access points. Be aware that your full height partitions, solid walls will reduce the effective range of your devices. So you'll need, at a bare minimum, a 20% overlap between access points. And this is where I was taking the point. So if we have channel 1 here, channel 6, channel 11, they're all on separate discrete channels, so they don't cause interference with the overlap. And then we come back to channel 1 on the right hand side, and this allows us to have our clear channels that don't provide interference to each other and provide full coverage. Excuse me. Our threats are basically data interception because of it being wireless. It's a radio. You tune into the radio with the right equipment, you can hear the messages. Other devices can join in if it's not secured properly. You can have denial of service attacks easily with RF jammers, for example, and you can have people plugging in access points without authorization, which is causing all sorts of problems, which is a rogue access point. So our denial of service can result from improperly configured devices, people interfering with the frequency, which is deliberate or accidental. So multiple ways of interfering. As you saw earlier, the microwaves were very close to the frequency that we use, so they can cause interference. All our other devices using 2.4 gigahertz can also cause interference, such as wireless headsets that are set to run on 2.4 gigahertz. There's wireless mice. There's all sorts of things that run in this range. Rogue access points is generally where somebody plugs in an access point because they feel they weren't getting the correct service from a wireless coverage point, and they've done it without the knowledge of the enterprise. They can be just people too lazy to plug in a cable on a laptop and bring in a device from home and hide it underneath a desk, or it could be a deliberate attack, somebody plugging in an access point to try to attack the network remotely. All sorts of different things can happen here. So if we are using controllers, we can have policies, policies that detect and know where the locations of all the various access points are, and we can monitor it. We monitor it via the strength of the radio signals, as we can see various access points to each other, and they can detect where there's a new access point turned on and give warnings. Man-in-the-middle attacks, as you know, is where we impersonate a authorized handler of information, and we send that information via them to be forwarded on. So wireless makes it easier for them, and they can impersonate a legitimate access point and have the information sent to them, or they can impersonate a gateway. There's various things they can do. Now, I don't like this one. The SSID Cloaking, they secure wireless, doesn't make it secure. Or what you're doing is you're asking your software on your client not to display your SSID. This, I hate it when they put it in here as a security thing. Basically, the idea is, as most devices conform to the request of not displaying the SSID, the users will not know that the service is there and won't be able to connect to it. Trouble is, you can tell the clients to ignore that request and display all beacon messages, so it's very low in the security scheme. Next is adding all your MAC addresses of your authorized devices into a table, and if you're not on the table, you don't get access. This is known as MAC address filtering, and as we've discussed in previous classes, MAC addresses can be impersonated, and spoofing attacks can be valid sources of trouble. Alright, our authentication, we can have open system. This is a polite way of saying there is no authentication required and you will connect straight in. Such as available from your airports, cafes and hotels. Now, this is a bit of an issue. Yes, it's open system. You can connect to the access point without authenticating, but you can't go through their proxy unless you pay them. So, yeah, they're not really the best source there for a demonstration of what open system authentication is. It basically says it doesn't have requirements from a wireless perspective, but it has back-end service requirements that is imposed on the connection before going further. Share key is the most common. That's the one you'll use on your home devices and even on enterprise networks between the wireless controllers and the radius servers where we're using enterprise authentication. So we have various mechanisms that provide this. We have WPA, WPA2 and the new kid WPA3, which allows us to provide passwords that are pre-shared between the access points and the devices. Wi-Fi protected access is WPA and the various versions, and wired equivalent privacy WEP was the very first one. Now this takes only seconds to crack now. WPA takes about 17. WPA takes a little bit more, but will eventually succumb. But it's a lot more robust. And then we now have the new generation coming online, which is WPA3 and requires the protected management frames. So it's slightly different in the way it works, and the security of it will last longer. How do we do it on a home device, on our domestic devices? So when we're going the wireless setup, in the security mode, we just select the type we want. So personal is where we have pre-shared keys. Enterprise is where we're using a radius server to authenticate against. Now the radius server is providing AAA services, and the user has to have an account registered on that server. So username and passwords, just like you would on a normal system. So it has to have your credentials already provided to it for you to authenticate against. Between the client and the radius server, it now uses 802.1x, which uses the EAP, which is Extendable Authentication Protocol, to provide that authentication message handling. Encryption methods that are available to us under pre-shared keys are TKIP. This is the older of the two, so please use the Advanced Encryption Standard, which allows us to have a larger, more robust encryption, and it will take longer to break. When setting up for enterprise, you need to tell it again what encryption you're going to use, but you then have to add the location of the radius server, i.e. its IP address, what port it's running on, and the pre-shared key that the access point and the server use to authenticate between themselves. So, why did we get WPA3? Well, we needed to up the authentication and encryption, as we have developed tools that make WPA more robust from the brute force attacks. Excuse me. And we now have the Internet of Things using device provisioning protocol that correctly connects. Alright, so in summary, we quickly discussed the concept of standards, which basically the same standards that apply in wired, apply in wireless, except we put W in front of it. WAN, MAN, LAN. Personal area networks are a new one, as far as those standards were concerned. So we talked about how they will use the various technologies, Bluetooth, WiMAX, which is microwaves, mobile networks and satellites to provide this, as well as Wi-Fi. We looked at the two common frequencies. We quickly discussed the three main organizations that influence us. We talked about how the wireless controller manages the access points, and we talked about how wireless uses radio frequencies and various channels within that frequencies to enable a clear conversation. We then quickly covered over the most common types of threats to wireless networks and some mitigation potentials within the wireless spectrum. That was a lot of time of me talking. I hope some of you are still awake. I'm having trouble staying awake myself. So that's the end of the module. The next session we'll go through the actual process of configuring various devices within the wireless network.